Welcome back to the next video. I left you on this example. We found the curl. The curl is non-zero for all values of x and y. That is, for all values x and y, the curl is non-zero. We found an integrating factor then. Since this simplifies to something we can separate, we get that u here is e to the y squared. This is our integrating factor, so we multiply everything by e to the y squared. 0 times e to the y squared notably is 0. And now we have an exact differential equation. We can solve this using techniques from Calc 3. I know the derivative with respect to x has to be x e to the y squared, so f must look like this: 1/2 e to the, or 1/2 x squared e to the y squared times at most some function of y. The derivative of this must be equal to this when I take the derivative with respect to y. And so that means my function has to look like this: 1/2 x squared e to the y squared plus 2 e to the y squared plus at most some constant, something which is constant with respect to x and constant with respect to y. We're looking for a level curve of this. So taking the level curve equal to 0, we get, now plugging in the point 0, 4, making sure this passes through this point, we get that c here is such that we have the equation e to the y squared times the quantity 1/2 x squared plus 2 minus 10. All right, let's shift gears a little bit. We're going to talk about matrices for a minute. This is Appendix 2. I'm going to begin by defining a couple terms. I want to define, given a square matrix A, we know we can find the determinant of that square matrix A. And if the determinant of that matrix is equal to 0, then we say A is singular. And what that means is there does not exist an A inverse. And if the determinant is not equal to 0, then there is an A inverse. I also want to define the transpose of a matrix. The transpose of a matrix is given that A is defined as A11, A12, all the way out to A1n, A21, A22, all the way out to A2n. All the way down to AN1, AN2, all the way out to ANN. Then we define A transpose A super T as being A11, A21, A31, all the way out to AN1, A12, A22, A32, all the way out to AN2, all the way down to A1n, A2n, A3n, all the way out to AN. What this means is we just flip it across that diagonal. What was on row 2, column 1 gets moved to row 1, column 2. What was on row n, column 1 gets moved to row 1, column n. We just flip it along the diagonal. Notably, taking the transpose of a matrix doesn't affect the diagonal entries. And I also want to acknowledge that nothing says the elements in a matrix must be constant. In fact, we've seen before, there are many matrices out there where the elements in the matrix are functions of some other variable. So if I have the matrix A, which is a function of T, this means that the matrix has entries, which are individually functions of T. On an M by N matrix, we can do calculus on this matrix. We can define the derivative with respect to T of A, which is just the matrix of the derivatives of the individual elements. Which is to say, if I have a matrix that has functions of T as its elements, taking the derivative of that matrix is as easy as we would like it to be. We just go through each element and take the derivative in the exact same way we took the derivative of vectors, of vector valued functions. And if I can take the derivative, I can also take the antiderivative or the integral. And this is, again, just the matrix whose elements are the antiderivatives of the individual elements. So we can perform calculus on the matrices as we would like to. So for example, if I give you the matrix cap X of T, which is the column matrix sine of 2T e to the 2T, we could find X prime of T, the derivative of X with respect to T. And this would just be, we're going to take the derivative of each element. The derivative of sine is cosine. The derivative of sine of 2T is cosine of 2T times the derivative of 2T, which is 2 cosine 2T. And the derivative of e to the 2T is e to the 2T times the derivative of 2T. And we can say that the integral from 0 to T of X of T is equal to, well, the integral from 0 to T of sine of 2T and the integral from 0 to T of e to the 2T, which we calculate to be negative 1/2 cosine of 2T plus 1/2 and 1/2 e to the 2T minus 1/2. So we can perform calculus on matrices in the exact same way we would really like to. Let's remember some basic operations on matrices. If I have the system x plus 2y equals 1 and y equals 1, solving this using algebra is incredibly straightforward, right? We already know that y is 1. I can plug that into the first equation and get x plus 2 times 1 equals 1 and find out what x is. But I could also write this as an equation using matrices. I could write the coefficient matrix 1, 2, 0, 1, since this is 0x plus 1y, times the column matrix xy, and I can set that equal to the matrix 1, 1. If I multiply this out, I get 1x plus 2y equals 1, and 0x plus 1y equals 1. If I have the system x plus 3z equals 2 and y equals 3, I could write this using the matrix, the coefficient matrix 1, 0, 3, 0, 1, 0, and that is being multiplied by x, y, z, and that is equal to 2, 3. And we remember, we can actually, since this is used so commonly, we have a different way to write this. We can write this as just an augmented matrix where we take the coefficient matrix 1, 2, 0, 1, and we augment that with the right-hand side of the equation. And this is understood to be shorthand for this entire equation. Similarly, we could write this as an augmented matrix 1, 0, 3, 0, 1, 0, augmented with 2, 3. And so we could take the augmented matrix 1, 0, 1, 0, 1, 1, augmented with 1, 1. And we could translate this to a system of equations using x's and y's. This is shorthand for 1, 0, 1, 0, 1, 1, x, y, z is equal to 1, 1, which gives us the system x plus z, 1x plus 0y plus 1z equals 1, and 0x plus 1y plus 1z equals 1, which we could clean this up, right? We could write this as x plus z equals 1 and y plus z equals 1. So let's use matrices now to solve a system of equations. If I have the equation 2x plus 6y plus z equals 7, and x plus 2y minus z equals -1, and 5x plus 7y minus 4z equals 9, and I want to solve this system of equations, I can, of course, use all of the approaches that I know from algebra, right? I can solve one equation for, say, z, plug it into the other two equations, giving me two equations with only x and y, and then solve those. I could just plug in values and hope for the best. What I'm going to do instead is I'm going to rewrite this as an augmented matrix. This is 2, 6, 1, 1, 2, -1, 5, 7, -4, and this is augmented with 7, -1, 9. And I would like to solve this system of equations. Now we can do, say, row 2 minus row 1. If I want to get rid of the 1 here, I could actually do row 2 minus row 1. That's going to give me a 0 here. When I perform this operation, the first row is going to be 2, 6, 1, still augmented with 7. The second row is going to be row 2 minus row 1. So 2 of these minus that. 2 times 1 minus 2 is 0. 2 times 2 is 4. Minus 6 is -2. -1 times 2 is -2. Minus this is -3. -1 times 2 is -2. Minus 7 is -9. And maybe I want to get rid of the 5 as well. So I'm going to do row 3 minus I could do 2.5 row 1, but I don't really want to deal with fractions. So I'm going to do 2 row 3s, and I'm going to then subtract off 5 row 1s so that I get 10s in both cases. So I get 10 of these minus 10 of those, I get 0. 2 of these, so 14 minus 30. 14 minus 30 is negative 16. Negative 8 minus 5 is negative 13. 18 minus 35. 18 minus 35 is negative 17. And I could, if I wanted to, retranslate this to x, y, z's. And what I would see is I get a negative 2y minus 3z equals negative 9. Negative 16y minus 13z equals negative 17. I don't really want to go back to equations. So I am going to, let's go ahead and zero out this entry as well. So we get an upper triangular matrix. To get rid of the negative 16 here, I am going to just combine it with this one. Say if I multiply this second equation by 8 and then subtract them, that'll get rid of it. So let's do row 3 minus 8, row 2. I didn't do anything to row 1, 2, 6, 1, 7. Didn't do anything to row 2, negative 2, negative 3, negative 9. But now row 3, I'm changing. This minus 8, 0 minus 8 times 0 is just 0. Negative 16 minus 8 times negative 2. Negative 8 times negative 2 is positive 16. Negative 16 plus 16 is 0. Negative 13 minus 8 of these. Well, that's a negative. Negative 8 times negative 3 is positive 24. Negative 13 plus 24 is 11. And then negative 17 minus 8 times negative 9. So negative 17 plus 72. Negative 17 plus 72 is 72 minus 17, which is 65 minus 10, 55. Let's clean this up just a little bit. I would like to turn these diagonal entries into 1s. So I'm going to, if I see, the easiest way to turn an 11 into a 1 is to divide by 11. The easiest way to turn a negative 2 into a 1 is to divide by negative 2. The easiest way to turn a 2 into a 1 is to divide by 2. In each case, the top two, I'm going to get fractions. So let's go ahead and continue zeroing things out first. So I'm going to get rid of this negative 6 by adding 3 of row 2. So I'm going to take row 1 plus 3 row 2. So I've got 2 plus 3 times 0 is 2. I've got 6 plus negative 6 is 0. I've got 1 plus 3 times negative 3, which is 1 minus 9, is negative 8. And I've got 7 plus 3 times negative 9. 3 times negative 9 is negative 27. 7 plus negative 27 is negative 20. Let's leave that negative 3 there for a minute. So I get 0, negative 2, negative 3, negative 9. And then I'm going to go ahead and divide row 3 by 11. So I get just 1 and 5 down here. Now I want to get rid of this. I may as well go ahead and get rid of the negative 8 and the negative 3. So I'm going to do that by combining it with the 1, 5. So I'm going to do row 1 plus 8 row 3. And I'm going to do row 2 plus 3 row 3. This will allow me to get all zeros in that column above the 1. So I get 2, 0, because this plus 8 of these, 2 plus 8 times 0, 0 plus 8 times 0. Negative 1 plus 8 times 1 is 0. And now negative 20 plus 8 times 5. 8 times 5 is 40. Negative 20 plus 40 is 20. and then 0, -2. -3 plus 3 times 1 is 0. -9 plus 3 times 5. 3 times 5 is 15. -9 plus 15 is 6. And 0, 0, 1, 5. Now let's make these diagonal entries ones. I'm going to do row 1 divided by 2, and I'm going to do row 2 divided by -2. I'm going to leave the third row unchanged. 20 divided by 2 is 10. And 6 divided by -2 is -3. I didn't do anything to the third row. Translating this back to our equations. This is 1, 0, 0, 0, 1, 0, 0, 0, 1 times the column vector x, y, z is equal to 10, -3, 5, which is equivalent to saying that x is 10, y is -3, and z is 5. Okay, I was able to solve this system of equations using matrices, using only row operations from matrices. Admittedly, this was not faster probably than using just the equations, because if we go back and think about everything we did, it's entirely possible our first step here might have been to take 2 times this equation and subtract it from this equation to get rid of x's, and then do 2 of this equation and subtract off 5 of this equation to get rid of the x's, and then I'm left with just 2 equations with y's and z's. I've effectively done all of my combining of equations. I'm just only using the coefficients. I didn't really save any time here. So let's switch gears. Let's think about this differently. If I let A here be equal to the coefficient matrix 2, 6, 1, 1, 2, -1, 5, 7, -4. And if I define x here to be my column vector of variables, x, y, z, and I define B here to be the column vector of the solution, 7, -1, 9, I've turned this equation into an equivalent form of AX equals B. And you can check that for yourself. You can set the A times X and see if you do indeed get the left-hand side. Set it equal to the B and see if you do indeed get the equations that we started with. We do. But now looking at this equation, like I'm left with A times a variable is equal to B. And if I told you something like 3x equals 6, well, you wouldn't do anything particularly astounding to this. You would just divide both sides by 3 and giving you x equals 2. So when I look at this, I would like to divide both sides by the matrix A. Unfortunately, division using matrices, not really something we're happy with. So let's think about this differently. If I gave you 3x equals 6, maybe your thought is, oh, I'm not going to divide by 3. I'm going to multiply by the multiplicative inverse. I'm going to multiply both sides by the multiplicative inverse of 3, because 3 times 1/3 gives me the multiplicative identity, 1. And 1/3 times 6 is 2. And so I end up with x equals 2 as the solution. And I never had to divide anything. I just had to have the multiplicative inverse. Going back to here, remember in matrices, I do have inverses of matrices provided that the determinant is non-zero. There is an inverse matrix of A such that when I multiply these two together, I'm left with the identity in the world of A, I3 in this case, because it's a 3 by 3 matrix. So if I could just instead multiply both sides of this equation by A inverse, I can avoid that whole discussion about, well, how do I divide matrices? Now I know A inverse times A is going to give me I3. And I'm going to table the thought of A inverse B for a minute and just clean up the left-hand side. So what I'm saying here, when I say I3 times X, I3 is the diagonal matrix with entries of 1, and X is the matrix X, Y, Z. So we can see I do indeed, if I was able to do this, I would get 1x equals, and then whatever the first element here is, 1y equals, and then whatever the second element is here, and then 1z equals whatever the third element is here. Of course, all of this hinges on our finding A inverse. There are a lot of techniques out there to find A inverse. They're not in the scope of this class, as this is not a linear algebra class. We just need to be able to find this. So what we're going to do, generally speaking, is we're going to input this matrix into our calculators. Either our TI-84s or TI-89s will do it. And then I can just type into my calculator whatever I stored as A, do A inverse and multiply it by my matrix B. And when I do this, I will indeed get 10, -3, 5 as A inverse times B. Again, finding the actual inverses of 3x3s is not something that's in the scope of this class. We will, for solving differential equations in this class, use our calculator to find inverses of 3x3s. The inverse of a 2x2 matrix isn't that bad. You can just look up the formula and use it, or you can derive it yourself. Doesn't really matter. All right, that takes us to the end of today. I will see you next class.